Hi, so welcome everybody. This is the second webinar in this Cardamom series. Cardamom, for those of you who aren't aware, is an Irish Research Council funded project based at the Data Science Institute at NUI Galway. And we're looking at how we can develop natural language processing techniques for minority and historical languages. So I'm very happy today to welcome Rolando Coto-Solano from Dartmouth College. Rolando has done a lot of work working with low resource and indigenous languages, particularly in Central America. So he's going to talk today about the Chibchan languages, which are extremely low resource languages, obviously, and some of the challenges of creating NLP resources. So I hope it's a very interesting talk, and I hope you all enjoy it.
Let's see. Awesome. Can you all see my screen?
Yes, we can.
Great. Good afternoon. Thank you so much for being here. Thank you so much to Priya Rani and to John McRae for inviting me. So, yeah, my name is Rolando. I am a professor at Dartmouth College, and I have worked with Indigenous languages for most of my career. So, I mean, as you all well know, and my understanding of the Cardamom Seminar Series is that we're here to, share our challenges regarding, low resource languages. What can we do to bring NLP to them, particularly deep learning solutions to them? And I've found that time and again, the way that I can make up for the very low resources in data is to try to make richer representations and more linguistically informed representations of these languages. So I'm here to tell you a few stories about linguistically informed representations and how they can improve deep learning for extremely low resource languages. And in particular, we're going to focus on a family of languages called the Chibchan languages from Southern Central America and Northern Colombia. There we go. So yeah, I mean, we all know Jean-Luc's phrase that when you fire a linguist, their accuracy goes up. There's a long history in our field of thinking that linguistic knowledge is irrelevant at best and detrimental at worst when you're trying to build natural language processing tools, and that our hope would be for these systems to be language independent, because of course it means that they would scale from one language to many. But as we all know here from work in low resource languages, this is just not the case. The fact that something is solved for English does not necessarily mean that it will work properly in other settings and languages. So I'm here to present two pieces of research where I'm trying to incorporate linguistic knowledge to improve the results from NLP. In particular, I'll focus on the transcription of tone and other suprasegmental features to improve speech recognition, and on how morphological tokenization can be used to improve the results from neural machine translation. But in order to do that, I first have to tell you not only a little bit about Chibchan languages, but also in the many challenges that we faced in preparing the data sets themselves. Again, as you all know from this, just doing something where you scrape from Twitter, where you collect chats from Facebook, it's impossible. And not only impossible because the data might not exist, but because the orthography might not be standardized, because people might use different dialects, and you might give primacy to one over the other in how you form your data sets and so forth. So I'm going to tell you a little bit about the languages, the process of preparation of the data sets, about some of the limitations we are facing when trying to adapt deep learning for these languages, and on how we have tried to improve upon these. And again, the two use cases that I'll focus on is how to transcribe tones for speech recognition and how to use morphology to improve the inputs of neural machine translation. Then I'll also tell you a little bit about some of the ethical issues involved in this kind of project and some of the issues that we still have to solve in order to make this project not only better, but more impactful. So This is Central America and South America. And these are the Chibchan languages. They're spoken, as you can see here, in Costa Rica, Panama, Colombia, and a few of them here in Honduras. So the greatest variety of the languages is probably found here in the Costa Rica-Panama border. So that might be their Urjaimats, their original homeland, where Proto-Chibcha was spoken. There's a few languages in the family that you might have heard of before. For example, Kuna is spoken here in Panama. So this has been one of the more documented languages in the family. Languages like Muisca and Duit have also been well documented in Colombia. Today, I'll focus on the languages from Costa Rica. So we have 3 living Chibchan languages spoken within the territory of Costa Rica. There's one that's trans-frontier called Ngabere, which is spoken between Panama and Costa Rica. But in this territory, for example, there's Maleku, which only has several hundred speakers. And unfortunately, it's highly endangered. There's Brunca and Teraba, which are unfortunately dormant at this point. But there are 2 languages that are still spoken, Cabécar and Bribri. So Cabécar is spoken in these red areas here. And by the way, there's a separation because this is a big mountain range. So speakers live on both sides of the mountain. So Cabécar is spoken in the orange areas and Bribri is spoken in the blue areas. And they are genetically related. They're very similar languages. Bribri itself is spoken by about 7,000 people. This is what the territories where Bribri spoken are look like. They are, lowlands, rivers, tropical. It's a vulnerable language, so not all generations speak them. Grammatically, it's a tonal language. We'll talk more about this in a moment, but it's like Mandarin Chinese, where the pitch of a word changes its meaning. It has inflectional morphology, so it has very rich morphology in the verbs. It has a lot of different tense and aspect endings. It has numerical classifiers like Japanese and Chinese, where you have to say, for example, 2 long objects of snake, but 2 buildings of house, and so forth. It has positional copula, so you can't just say that something is on the tree. You have to say that something is hanging from the tree. You can't just say that someone is in the house. You have to specify whether they're lying horizontally in the house or standing in the house. And it has ergative morphology, same as Basque, for example. So as you can see, it's a language that is structurally fairly different from Spanish and other languages that might have a lot of NLP resources. So in the last decade, there has been an effort to try to create tools for natural language processing in these Chibchan languages. The pioneering work in this is Sofia Flores's keyboard for Chibchan languages, which, as you can see, is a very practical tool to allow people to chat in the languages, to use the phone in the languages, write email, and so forth. So it's a package to map the many characters that are needed to write Cabécar and Bribri into mobile keyboards. You can see, for example, that there's a line underneath the vowels. This is the nasalization. This diacritic here is for the high tone. So this is shkena. And there's combinations of keys that will help you get to that. Recently, I've been working in helping make predictive text. So improving upon these applications so that you can type and the correct diacritics will be predicted for you and so forth. This is a project that's still in progress. There has been effort in lexicography as well. So Hakon Kron, for example, has been compiling a digital dictionary of Bribri. This is amazing work because he's gone back to old sources to try to figure out if the sentences that were compiled in them were correct or not, to try to refresh and make the dictionary anew. Guillermo Gonzalez is working on making a small glossary in one of the dialects of the Cabécar language, in the Chiripo dialect. It's work in progress, as you can see here, but they are both available online. And there has been work on generating corpora for the language. So Sofia Flores, as part of her dissertation, made a corpus and also finite state transducer to get the grammar of Bribri to, for example, figure out that the word cerque, which means to live. This is my name is Sophia and I live in so forth. Cerque means to live somewhere, and it has se, which is the root of the verb, the R, which is something called middle voice, and the que, which is the tense for this particular sentence. So this FST attempts to break down the word into its component, into the description of its morphemes. And she created a big corpus with this, including recordings, which we used for the automated speech recognition. Using these tools, we have also tried to make more sophisticated tools to, for example, study the phonetics of these languages. So I did an experiment a couple of years ago to try to use untrained forced alignment for Bribri, Kabekar, and Maleku. So in untrained forced alignment, we use a speech model from some big language, for example, English. And we take advantage of the fact that a K in Bribri, for example, is relatively similar to a K in English. An M in Kabekar is also similar to an M in English. So we run the sounds through, for example, an English sound model, get a rough transcription, and then we modify the language model, the dictionary of the output. So we tell it that essentially there is now an English word, which is whim, which means monkey, which is composed of the sequence woo, e, and then we perform a bunch of behind the scenes calculations to try to retrieve, recalculate what the tones were and what the nasals were, which are lost in the process of listening to this as if it were English. It worked better than you'd expect. So the error was of about 7% in the position relative to the center of the words in aligning the words with the sound signal, and of about 24% of the length of the vowel in aligning to the center of the vowel. So the A might have been here, or maybe a quarter of the way off here. And we've used this to study more about the tonal phonetics of the languages. We've also done experiments with neural machine translation. So yes, this is where it starts getting interesting. We compiled a list of about 6,000 parallel sentences in Bribri and Spanish, and then we tried to run it through a transformer. We used the package OpenNMT to try to figure out if it could do anything with the 6,000 sentences. Surprisingly, again, it was better than you'd expect. We have a sentence in English, in Bribri, "Beriesun," which means you saw it. You saw him or her. And the Spanish reference was "Usted lo vio," and it managed to translate the Bribri into Spanish. For some of them, it still has problems. For example, in Bribri, the third person pronoun does not have gender. It can be he, she, or singular they. And of course, it gets it wrong quite often in the Spanish. So this was, for example, supposed to be ella. And you could know this in theory from the context because Ana is a feminine name, but the system gave us él se llama Ana. He is called Ana. But again, with 6,000 sentences, we were surprised it even kind of worked. So this is the brief summary of the work that we've done with natural language processing for these languages up until 2020. I want to tell you a little bit more about how we compiled those 6,000 sentences, because I imagine these are challenges that you are all facing as well. So creating this corpus entailed extracting information from wherever we could find it. And there is a dictionary of the language. There's 2 textbooks written by different authors. There's the grammar, there's a storybook, there is the corpus that I mentioned before from Sofia Flores, and there's some other books, for example, some books published by the community, by school teachers, which we're still trying to bring into the corpus. We used a few of the sentences because you'd think that being published, these materials are fairly standardized, but you would be wrong. There was a lot of variation in the data. For example, different authors have chosen different writing systems. The representation of the nasal is different for the author of one of the textbooks, another one of the textbooks, and the dictionary. So you can see this is a word that means cooking pot. It is nasal, high tone. The nasal is represented with a line underneath in one of the orthographies, with a tilde in another one of the orthographies, and with a Polish hook in yet another one of the orthographies. So standardizing all of these was something that we had to take into account for, for OpenNMT not to go crazy when it was analyzing the data. Again, even when you go deeper, there's more challenges that appear. The encoding itself is not standardized. So sometimes you would find this as a combinatory grave accent, and a combinatory low line. Sometimes you'd find them the other way around. There's another symbol which looks a lot like the low line, which is the minus sign below with a different Unicode, and I've found that as well. You could have this as a combination of the U with the grave accent, and then one of these, or this one, or other combinations of them. So I had to take that into account when building the corpus as well. And those are mere details. Where it gets really challenging is in the stuff that has to do with language and the politics of language. For example, this word here, ami, is mother. These two vowels become nasal because of the contact with the M. They're not underlyingly. The first one is not underlyingly nasalized. The second one, I don't think it is either. So, ami, you can mark the nasals explicitly or not. Some authors do, some authors don't. This first a becomes a really short schwa if you say it quickly enough, or if you're writing quickly enough. So ami can become mi for mother. And some authors have the a, some authors don't. There is a bit of sociolinguistic variation. So remember that I told you that the languages were spoken on two sides of a mountain. So this means that there are several dialects of it. So some people say ñara for road, some people say ñoro for road. And in addition to this, there's a lot of intra-speaker variation, again, because the language is not standardized. So many of the authors try to be consistent within their materials, but sometimes, things go one way or the other. For example, taye, which means a lot of something, can be found in many different ways. One of the most divergent ones I've found is, for example, taye, a lot of. So you'd have to build in some kind of way to make sure that these two are understood as the same by the computer. Dor sometimes found as ror, but this is not because of a phonological rule, is because sometimes the author hears it that way and writes it with an R. So I came up with a solution that has worked, but it also has challenges of its own. I came up with a sort of intermediate transcription so I could read all of this variation and have it, for example, mother is mi, with this as the indication of a nasal on its own, and this is the indication of a nasal with a tone. This is a good computer transcription. It does not create a lot of byte level confusion, and it can be converted to the more predominant orthographic representations of the language. It also has one important effect. It doesn't give primacy to one dialect over another. So, for example, this orthography is mainly used on the southern part of the mountain. This orthography is mainly used on the northern side of the mountain. So having specified that we're going to use this within the computer and then we have to convert to your preferred form is a way to try to make the system more dialect agnostic, if you will. Yes, it has the problem that there were two standards and now I've introduced a third standard. I am painfully aware of that. But it is the solution that we have found and that has worked for us in building all these tools. Let's see. So we did this with the 6,000 sentences. We compiled our corpus with that had a fairly regular representation of the tones, the nasals, and so forth. And then we set forth to try some deep learning experiments. We've tried some things that were more language independent, for example, for forming natural language inference and doing transfer learning from other languages in using speech recognition. And we have also done work where we use linguistic knowledge of Bribri and of languages in general to improve on those results. The tone transcription and the morphological decomposition, as I mentioned at first. So let's look at these two first. One thing that we created along the way is a resource that is now online called America's NLI, where we took some sentences from the XNLI corpus and translated them into a number of indigenous languages. So very quickly, NLI is natural language inference. It's the capacity of seeing two sentences and then figuring out what's the relationship between the two. For example, and he said, "Mama, I'm home," versus he told his mom he had gotten home. Are these two sentences neutral towards one another? They have nothing to do with one another. Are they contradictory to one another? Or do they entail one another, which means that essentially their meanings are similar. If one is true, the other one is also true. So these are the three relationships that you can have: neutral, contradictory, and entailment. We translated a corpus for Bribri of about, as you can see, 750 for development and 750 for testing of pairs of sentences from the multilingual NLI sets. You can see an example here. And he said, "Mama, I'm home." He told his mom he had gotten home. Having created this corpus, we tried to figure out if we could do natural language inference with just those 6,000 sentences as a kind of pre-training, and then these pairs as a kind of fine-tuning of some deep learning system. There was an architecture based on a Roberta and some BERTs, which it worked well. So it's called Translate Train, where we take the original 6,000 parallel sentences to do a back translation, a way to get Spanish sentences translated into Bribri so that we can translate more sentences from the XNLI and use them to help train the inference system. And this worked better than chance. So if it was chance, it would be 33%, which means that because it has three options, it's going at random between the three. But the performance so far has been 52%, which means you're getting it right about half the time. So it works, but it can evidently still be improved. I've also performed experiments with speech recognition. In particular, this one, I tried to take the deep speech system, which is an end-to-end speech recognition system, which uses CTC as its learning algorithm, and then try to take the final layer of the neural network off to then replace it with a layer that's trained for Bribri. So what this algorithm does is that it has a number of neural network layers that learn the audio of, for example, English, and learn to understand the audio of English, and then we replace the final layer, which transcribes the sounds of English into the words of English, and replace it with the words of Bribri, in the hope that we will be able to get this knowledge of the sounds of English to transcribe words of Bribri, for example. This experiment is performed on Bribri. It didn't work. Giving the data as is generated errors of 100% of word error rate. It means 100% of the transcribed words were wrong. CER is character error rate. About 86% of the characters that were transcribed by the system were wrong. If I just, agnostically tried to get the deep speech to use its knowledge of English sounds to then transcribe the words of Bribri. I tried it with Mandarin as well, and I thought it would work better since both languages are tonal and their tones are not that dissimilar. Interestingly, it was worse. I don't quite yet understand why. The tones are not that different. I'm guessing the phonemes themselves might be different. It might also be a difference in how much data it was used to generate the models originally, although the deep speech Mandarin model is fairly reliable. So this is another example of a system that's not quite working yet. And the thing in common between this one and the NLI system is that they were both just throwing the data in without any previous preparation, in the hopes that we make essentially a sequence-to-sequence, end-to-end system. So I want to tell you about two experiments to bring linguistic knowledge into deep learning training. The first one has to do with tone. So Bribri, as I mentioned, is a tonal language. What does that mean? It means that differences in pitch can give you differences in meaning. So for example, Bribri has the word ara for child and ara for thunder. So you can see that this final syllable is high tone and this one is falling tone. Ara, ara. There's high tone, falling tone, rising tone, and the most common tone of them is just a low tone, wa. For example, this word means with. There's also an underspecified fifth tone, which is neutral, which mostly manifests as low, but it can also be mid, depending on whichever tone happens next. But very importantly, in writing, this underspecified tone is indistinguishable from the low tone. There's neither of these two are marked in the writing. So yes, we have tones. Bribri has another interesting feature for the vowels, which is that it has nasality as a way to distinguish meanings. If you studied French, you're familiar with nasality. For example, ou versus un. House and pot are different words, and they both have the ou vowel. They have high tones, but one has an oral vowel and the other one has a nasal vowel. So what do we have? We have the feature of tone, the feature of that one of them is the most common tone, the low one, and that we have nasality as a way to distinguish between words. A word that would have all of these things together would be the ki, which means the area underneath something. This first vowel is low, this second one is high tone, this one, and the vowel at the end is nasalized. How do you transcribe the ki? You'd think the answer is more straightforward than it is. The truth is, there is no consensus in speech recognition of exactly how you should transcribe tone. In languages with enough resources, the most likely thing you'll do is try to get the system to learn the tone together with the vowel, because it is very likely that these two are indicated together in the orthography. This will be the case in pinyin in Mandarin, where the vowel and the tone happen in a single grapheme, likewise with Vietnamese. So in many systems, you just leave these two together into transcription and feed that into the system. Another way in which this could be done is that you can have some way of separately processing the tone and the vocalic quality. This is something that has been tried for low resource settings. For example, for the Na language from China and the Chatino language from Mexico. They have tried representations that have the vowel and the tone transcribed one next to the other, for example, to try to see if the computer learns them separately. And by the way, they do this by transcribing it into IPA. There's some ASR systems where the tone is not learned at all. For example, in ASR in Hausa, it's not represented in the written input to the system. So how can you transcribe a word like Diki? I performed an experiment to try to see how some of these combinations would work out. For example, you could provide a transcription with 4 characters where essentially the vowels and their features were represented together. So you would have the D, the I, which is low tone, the K, and the I, which is nasal, which is high. This again would essentially have 4 characters. And in total, you'd be learning about 48 different characters for vowels and their combinations of features. And the other end of the spectrum, you can have a transcription where, I'm sorry, let me start with number 2. The nasal is separate from the tone. So this has 5 characters, D, I low tone, K, I high tone, and the nasal representation separate but together with the vowel it co-occurs with. You can have them all separate. You could have the D, the I, the low tone, the K, the I, the fact that there's a high tone in this vowel, and the fact that there's a nasal here. Notice that this would give the system an input of 7 characters, and you'd be learning only 12 different characters. Pretty nifty. You could also keep some things together and some things separate. So number 6, for example, keeps the nasal together with the vowel. And so we've seen some permutations of how the nasal can be represented. It can be linked to the vowel or separate from the vowel. We have seen some permutations of how the tone could be represented. It could be linked to the vowel or separate from the vowel. And there's a third thing that can be done. We could choose to represent the most common tone or not. So notice that in this final representation, we have the D and the I, and then there's nothing. So we're not telling it to find any tones there, assuming that, you know, this is going to be like default I. But we're telling it for the second one that this isn't like a default tone, that this is in fact a special high tone. So you can see that all permutations have slightly different numbers of symbols. You would think that, oh, I mean, which one's going to be easier? Maybe the one with the lowest number of symbols, because it has to learn fewer things. Maybe the one with the highest number of symbols, because everything is set, you know, in its little box, and then we could just focus on what makes an I nasal high, I nasal high. I set out to test this. I took the 68 minutes of transcribed Bribri speech from Sofia Flores' corpus and ran it through 2 different systems. Traditional speech recognition architecture with hidden Markov models and Gaussian mixed models, the CALDI package, and through an end-to-end, more contemporary CTC speech recognition system, Deep Speech. For each of the permutations in the previous slide, I ran it 30 times, randomly shuffling the training, dev, and test sets. And I'm going to present to you a summary of the results. The summary of the results is that separating the tone leads to better learning. As you can see here, as expected, the traditional older systems performed better because they can learn out of less data. This is the nature of statistical learning. But our error rate for characters was only 33% if we separate the tone, but, for example, keep the nasal with the vowel. Compare this, for example, 35%, by the way, which is a significant difference because we managed to run it enough times to compare, where the performance is not as good. And 42%, where everything was separated, including the nasality. So let's step back a little bit. What does this column mean? First of all, it means that if you separate the tone, you're getting the computer to get one chunk of the audio signal dedicated to the vowel information, and then another chunk of the audio signal dedicated to the tone. And this makes sense when what we know from tonal phonetics, in the beginning of the vowel, you get a period where your vocal cords are aiming at the tonal target. And it takes a little while, between 10 and 20% of the duration of the vowel, for the tone to actually be fixed in its location. So it makes sense to use like the beginning part of the vowel to decipher the vocalic information, and the later part to decipher the tonal information. Notice that if we separate the nasality as well, our performance gets worse. If all features are separated, our performance drops by almost 10%. Probably the nasal vowels are different enough from the oral vowels that they need to be learned separately. But the tones are similar enough amongst themselves, their pitch trajectories are stable enough that they can be learned as single units. Notice that having explicit versus implicit low tone also makes a difference. So implicit low tone means that I am not telling it to look for low tones. I'm sort of setting that as a default. But if I tell it explicitly, go look for low tones, its performance gets worse. This might be because of that phonetic variation I told you about, that sometimes the low is a phonological low, and sometimes the low is an underspecified that dances around between low and mid, probably leaving something as, you know, like the leftover tone where you're going to throw everything that you're not sure about is helping the system improve. Interesting. So these are the results for the Kaldi, the older systems. Interestingly, if you go to the actual deep learning, there are still differences. So the performance is much worse, as expected, because you need a lot more data to learn in these systems. The performance is worse, but there are still massive differences depending how you transcribe things. And here, all features separated and telling it to explicitly look for the low tone has much better performance, both for systems that were only trained on Bribri and for systems where you transfer from English. So let me show you some examples. First, I'm going to show you the deep learning ones and then the traditional ones. Why did separating everything and telling it to explicitly look for the low tone help the deep learning system? Probably because it helps it to keep listening. This is an example sentence. So you were young then, right? What the system gave us as the better output, which was separating everything and having the low tone, was eta ye, which it means it tried to listen and stuck with it for a bit, and then it gave up. It went on for much longer than just any of the conditions where the low tone was absent. In these two, I did not tell it to explicitly look for the low tone, and it just tried the first word and then gave up. It is probable that by telling it that every word has a tone that it has to attend to, this is pulling deep speech further along the line and making it listen for a little bit longer before it gives up. So in deep learning, telling it that all the tones are there appears to work in you know, keeping it listening. As for the traditional systems, the better conditions were the ones where I did not tell it to go look for the tone. And again, this might be because of the nature of the older systems. These were all trained in triphone combinations. So essentially, instead of the triphones being, you know, consonant, vowel, consonant, now one of the components of the triphone might be dedicated to listening to some explicit part of the sound, the signal devoted to tone, and then something devoted to vowel, and then something to tone, and then something to consonant. And as you can see, these perform a lot better. So eta pepa aquí at tsitsiwake was transcribed almost perfectly by the condition where only the tone was separate. Eta pepa aquí at tsitsiwake. So the error was, let's see, and it couldn't separate the word boundary between these two. In this one, where all the features were together, it couldn't hear this pronoun, be, which means you. And when everything was separated, as you can see, it made some mistakes, which were expected. Chichi means dog, and it kind of sounds like tsitzir. Wake means right, and it couldn't hear the whole thing. So again, the take home from this is that because of the behavior of the older systems, where they split the signal in triphones, for example, we now dedicate more attention to things like tone, because we tell it to explicitly go look for it by separating it from the vowel representation. Here, again, because the system is more end-to-end, it has much less data, but at least listening to the tone keeps it going, which is not necessary for the older systems. So some transcriptions are more helpful than others and can make a difference. Again, take home from this is separating the tone from the vowel makes it so that the system can pay more attention to the tone. Can adding linguistic knowledge to a transcription also help in machine translation? And explicitly, if we gave it the system information about the morphology of Bribri, will this help us? So Bribri and Spanish are fairly morphologically complex. They're not polysynthetic, but they're inflectional, but they do have some complexity in them. For example, the sentence, I did not sing, jekitsini, has a verbal root, st, and then the indication for the past tense and the middle voice. Spanish has inflections as well. Yo no canté has a final vowel for the tense aspect and root. I saw two snakes. So here, the verb also has a suffix for its morphology. And bottom means two long things. This is the classifier system that I was telling you about. So in Bribri, you have to say two long things of snakes and so forth. So both of these languages have complex morphology in them. And we know that when we're doing machine translation, the machine translation benefits from tokenization, which is as simple as, separate words by spaces, which we know from handling speech recognition in Chinese and Thai and Japanese. So some form of tokenization definitely helps. And ideally, you'd want a tokenization with units that make sense. For example, one potential way to transcribe this would be to split the words into the roots and their morphemes. J, K, S, and then that's one word. E, different word. Ne, different word. And then the system would learn meanings for each of these units. Likewise, separation of the Spanish like this would also make sense. Cant, e. One thing that authors have found is that in low resource environments, most of the tokenization algorithms that people use don't quite work. There might not be enough information for them to learn how to learn properly what are the morphemes in the language. For example, this is done with byte-pair encoding, with BPE, in some of the 6,000 sentences that we have. And this is the Spanish side. So this means there are, like outside, there are 5 tigers. And the system learned that fuera could be 2 different words. This would be the equivalent of splitting the English outside and outside, which doesn't really make sense linguistically. My last name is Lopez, which, as you can see, that's a Y. The system is trying to separate the L, the O, and the Pez, precisely because of the way BPE works. It's trying to find the most common combinations of characters in the sequence. But in doing so, when it has low data, it rips morphemes and words apart. Ideally, you would have a division that looked like this. Je cerque. as we showed at the beginning of the presentation. I live in Talamanca. But the truth is, when we looked at what the system was doing with our 6,000 sentences, it was ripping them apart. So it could not see that Serke was composed of 3 elements, but it tried to split this proper name, Talamanca, into a bunch of units that made no sense. And this, of course, was detrimental to the performance of the system. So by the way, this is an experiment that you know how when you give a talk, you try to, get something exciting and new, and you go and perform a new experiment. This is a fresh experiment that I finished putting into the presentation last night. So you're the first that are going to hear about it. There's obviously many ways to tokenize sentences. So I tried regular byte-pair encoding, also tried word piece and sentence piece, which have different approaches for how to split them, but they, in general, language independent. They are only looking at the most common sequences of characters within a string. There are tokenizers that are morphologically oriented, for example, Goldsmith and the Morfessor system. They take, for example, some morphological universals into account as they do the splitting. For example, Morfessor makes assumptions of what words are. For example, that words are likely to have a root and an ending, for example, or root and a prefix. So it goes and looks for units in those locations as opposed to everywhere in the string. In order to compare this, I also made a rule-based system based on the FTS from Sofia Flores with about 214 rules. As with any rule-based system, it has great precision, but very low recall. It means that the words that it split were split really well, but there's a ton of words that it should have split that are not visible by the algorithm. So I tried to run our 6,000 sentences through these, and also through nothing at all, not tokenizing them before putting them in the machine translation. Again, our 6,000 sentences, we use 3 systems that are relatively language independent. 2 of these that are language independent, but morphologically oriented in the way they split sentences. The rule-based system that we devised, and no tokenization as a control. We ran 30 experiments with random shuffling, and we did this in 2 different ways. We either had the tokenization in both the Bribri and the Spanish, or only in the Bribri without splitting the Spanish. And of course, no tokenization at all, has no tokenization on either side. So again, the systems that have incorporate some universal knowledge of what morphology looks like in human languages beat the more general systems. Morfessor had the character F performance of 39.5, which was better than the handmade system, the rule-based system that I made, and the Goldsmith one. And they all perform better than the more language agnostic ones, and then compared to the control. So, by the way, they were also statistically significantly better, the Morfessor, than the control, the no tokenization, and the rule-based system. What does this mean? And again, if you look at the tokenization, as we did with the case of Talamanca, it means that these systems are giving the computer better inputs to learn from. And with VPE, this has been studied previously by Sandvik, for example. Low resource settings can be terrible on your morphemes, and the algorithms that work for English or French are not necessarily going to work, particularly for languages that are more morphologically complex. So this is another example where some transcription of the initial input can be more useful than others and can generate real and significant improvements in the performance of deep learning systems. And again, this is with Open NMT, which is based on transformers, so it's deep learning. So very quickly as a conclusion, these are interesting systems. We're on our way to making them work better, but of course, these are nothing but toys unless they actually have an impact in the lives of people who speak the languages. We are trying to make these systems so that they can perform functions for the speakers. For example, we used many of the all the sentences that we compiled to make lexicons so that we can adapt them for the predictive text applications for the cell phones. This is an example of a tool that is actually necessary for the community and they've asked for by name. But in general, these tools that we design need to have a positive impact so that there's a relationship of reciprocity between the researchers and the communities. It cannot be the case that this is just merely extractive research where we take the information from Bribri, do fun NLP stuff with them, and then the info does not come back to the community. When possible, for example, we are starting a project to try to get the speech recognition to work better and to work with other languages than Bribri, for example, Quebecer, and this responds to goals of the community, goals of making materials, transcribing stories, and in order to do these quickly and efficiently, we need systems like speech recognition. And in general, one weakness of this project, which we're trying to overcome, is sustainability, in that we need to train members of the community to do the programming themselves. This is a priority which we're trying to work on, trying to have workshops in the community where we can teach people to initial Python programming and get them interested in this. There's one problem which in your work, I'm sure you've noticed as well. The main people who are interested in these things are probably language teachers, high school teachers, who are the busiest people on planet Earth. They are already working as hard as they can. They do not have time to learn anything else. We're thinking maybe we can recruit, kids coming out of high school to be interested in this. So we're trying to plan workshops for that. I'm working on a project on the other part of the world where I'm working on the Cook Islands, where this is we've done more progress on this. There is a better circle of accountability where school teachers have helped us with inputs for the speech recognition systems. We presented to them, and they've used this in their classes of linguistics of the Cook Islands Māori. For example, we made a part of speech tagger that they used to study the grammar of the language. This circle is more advanced than that one project, but we have to work harder on this for the Chibchan languages. As a quick conclusion, so hopefully these I've accomplished the goal of the Cardamom project, which is bringing you examples of how deep learning can be applied to small languages, indigenous languages. I brought you examples from language inference, neural machine translation, speech recognition, how some of them can be used with other statistical techniques, for example, traditional style speech recognition, and how they can be used to generate useful tools, for example, lexicons for predictive text applications. Hopefully I've given you a piece of evidence that there's plenty of room for linguistics to have, for linguistic ideas and linguistic descriptions of languages to help in improving the results of natural language processing, particularly for these languages where we have this knowledge and it can help make up for the lack of data to train. And there's still so much work left to do, and we're continuing our work on Chibchan languages, and hopefully this has been interesting to you. And there's so many people to thank, but in particular, thank you to the Bribri collaborators and co-authors, Adi Garcia, Francisco Morales, Carla Jara, one of my teachers of Bribri, and to everyone who has worked on me on these projects. And thank you to all of you for being here.
Okay. Hi, a really interesting talk, and it's good to know that we don't need to fire linguists, eh?
Yes, please don't, not yet.
No, definitely not at all. Okay, so I'll open the floor up to any questions. You can put it in the chat, or just raise your hand or turn on your mic.
I might have a question, John.
Okay, go ahead.
Hi, Professor Coto-Solano. It's really fascinating. I'm actually a postdoc on the project in Cardamom, and I'm actually a linguist, so I feel very safe now. But my question was on the, so you have a limited corpus of parallel sentence, but you also have a finite state transducer, so you could technically augment the corpus with synthetic sentences? Yeah. or use it in some way or another. I don't know how much the finance data transducer can do, how productive it is, how much it can generate. But you could, have you looked at this, or to augment the data you have, limited data you have, or? So
let's see, I tried, we definitely have tried back translation to augment the data set. We actually, in the paper where we did the 6,000 sentences, the original paper was about back translation to improve it, and it helped. So it improved to the blue translation by about 1 point. It was not amazing. Like they are, to be perfectly honest, these back translated examples were good to increase the knowledge of the system, but they are not realistic sentences of Bribri. And so we tried that one. We have not tried generating new sentences from the finite state transducer. And in any case, they would be monolingual sentences, which can be used for example, generating all the lexical forms in the text prediction. So our tests with the text predictor are ongoing. We have several people trying our current beta. We made it with the Keyman software, and so it's available online if anyone wants to try and download it. We haven't gotten to the point where people have said, oh, this conjugated word exists but wasn't there. I imagine it must have that weakness, as you described, that the corpus that we used it with did not include every conjugated form, and so an FSD could be made to alleviate that. Yeah, no, we haven't tried it, but that's a great idea. Thanks. And
well, I suppose it's a word-based tool, right? You can't create sentences with an FSD, I suppose. So it is. I'm not sure. I wasn't suggesting that you should do it exactly like this. Maybe it could be of assistant in some way or another. I don't know.
Yeah, no, I'm trying to think. So it could, for example, it can generate monolingual information, which can help us with the language models. So obviously, all the CalD results use a language model in the end, which is why the word, to be perfectly honest, it's why the words look Bribri, and it's why the deep speech is in the end so bad. Even the deep speech is using a language model, and I tried augmenting it with words that were not in the data set. So I tried several training combinations. One of them was the traditional ASR, which is use the words in the lexicon the sentences in the lexicon to generate a language model. And I also used another experiment. I can't remember the author right now. Someone was working on Komi, a language from Northern Europe, and they suggested augmenting the language model with more monolingual data that was not present in the ASR training set, but that could help with learn more relationships of the language. I tried giving it all the monolingual data we have, because we do have about 1,000 sentences that we haven't translated yet. It didn't work as well. I mean, maybe because it was the deep learning speech recognition, I didn't see any improvements. I haven't tried it in the CalD, but this is, as you mentioned, Professor Fanson, this is another way that it could be used to generate monolingual data to improve language models. Let's see. What other ways can we use the FST data for? Spell checking and language model making.
Good question.
Yeah.
Maybe someone else can. I'm just a linguist, you know.
Yeah. No, I wonder. I mean, surely. I mean, of course, there's a million ways to improve upon this. I also I really want to hear stories from all of you, because I imagine you all have many of the same challenges that I'd love to know how you worked through all of these. Costa Goswami.
Yeah, hi, Professor Solano. So I'm doing my PhD under John, and my research domain is very, same that you are working on this under-resourced languages. So I have two questions. This is very interesting talk. Thank you for this. I have some of the experience of this language models and others, and especially if I think about this XLNI dataset or whatever natural language inference datasets, these are not typical classification datasets. These are most of inference datasets. So what I was thinking, when you got the 52% accuracy on this very under-resourced language, I thought you told about that this model is actually the Roberta language model that you have trained, I think.
Give me a second, because I am because I did blank on that. Give me just a second. So I get you the exact specifications of it. So here's the, I'm gonna paste here the archive article in the chat window. It's XLM. It's XLMR. I'm so sorry. Yeah.
Yeah, so that's XLMR is trained with 104, and I don't think Bribri is there in the XLM model. So it's very interesting to see that it's actually performing good when unknown language has come down.
It's so strange, right? That it did anything.
Yeah. So
Yeah.
that's what I was thinking. Like in case of Swahili dataset, which is a very, very under-resourced language as well. In case of natural language inference, it just shows that though it is trained, XLM is trained on that language, it actually shows that it is 60 to 61% accuracy.
Wow.
So my question is, like, do you think that language biasness, the character, some kind of, in case of the tokenization, the sentence with tokenization, whatever it is for the XLM, did help the model to understand about the same kind of language that has been shown to it? Like some kind of tokenization might be same with some other language for Bribri, maybe Spanish or something, I don't know. So do you think that actually helped? And the second question is, when we are talking about the BP or the byte pair encoding, I understand that there is a paper which says that the tokenization, if the tokenization is very, very, have a good knowledge about the morphology, the model will be better. So do you think that if we make a very good tokenizer, which actually understand the morphemes or the roots, can actually help these under-resourced languages where only 6,000 datasets or 8,000 datasets, 8,000 sentences are there for a corpus to train a language model?
Let me go one step at a time. Oh, no wonder I thought of this. So yes, so XLM is based on Roberta. That's what I remember. The specific one was XLM. Let's see. Your first question was, so I'm reviewing the paper. It used sentence piece with the XLM. So it must have. I mean, because it was a zero-shot task, what else could it have gotten that would help it other than trying to split morphemes and stems as best as it could? And it was also, there were so many other languages. There was, I'm looking at the list, Shipibo, Wirarica from Mexico, like Aymara and Quechua from Peru. It must be using the tokenization to learn a little bit, because otherwise it couldn't. And by the way, interestingly, if you look at the paper, Bribri was one of the worst performers. So if you have more data, for example, the Guarani from Paraguay, for which they really had a data set that was at least, I want to say 10 times larger. Let me check real quick. The Guarani is, so the training was the same, but the original data set was 26,000. So 4 to 5 times larger. It must be the case that the tokenization helped it learn, and that's why you're getting much better results in Guarani. As for, let me see, BPE, can morphology
so my question was, if we make a tokenization system which actually understand the morphology or the morphemes better, will it help the underlying language models to do the pipelining, natural language inference, or any kind of processes?
My hypothesis would be yes, because it will get units that make sense. Like from our knowledge of linguistics, it's just and to be perfectly honest, I first noticed this when I looked at the transcriptions for the NMT, because if you install like OpenNMT out of the package, the default is to do BPE. And I first ran it to experiment with it, and when I noticed what it was doing, it was only then that I went down the rabbit hole. And Senrich has commented a bit on this, and the fact that with little data, it cannot learn enough. I imagine if it learned morphology, it will work better because the units will actually make sense. In these preliminary results here, it does make Bribri better. I can see from examining the data visually that the splits are a little bit better. It's just so difficult to scale. Like, as you well know, like I'm lucky that there are good descriptions of the Bribri language to do the rules, but imagine if you're working by yourself on a language where you're writing the grammar and also doing this. It's so expensive to scale them. So at least we can use these morphologically informed, more language agnostic algorithms to improve our performance. And as you can see, the professor did, again, better than I expected. I imagine the ideal would be to have like a morphological analyzer for each of them, but it's just it's so expensive and difficult to make. And I bet you all of you are like already overworked and tired and don't even know, like, I have 10 things to do in this language. What am I gonna do? Yes, so my hypothesis would be yes. I have results that indicate that it is yes. I would definitely encourage you to try more language-oriented tokenizers and let me know how it goes. Does that answer your question?
Yeah. Thank you. Yeah.
Okay, thanks. Yeah, so I have a question as well. So I was very interested to see that in the ASR transfer learning, English actually did better than Mandarin. But maybe I'm also not too surprised because in terms of the phonetics, Mandarin has a lot of things like kind of the aspiration instead of voicing in Mandarin and
this is true.
onset. So, I was wondering if you had any insight into what are the features then that made the English model better, and then did you try it with other languages? Maybe there is a language which transfers more naturally into Bribri.
So I haven't tried it with ASR. I can tell you that when I started this, in the forced alignment, I tried French because I thought nasals, maybe it'll help. It didn't. English was better. And when that happened with the forced alignment, I thought maybe it's just a matter of English has more data, so it knows the sounds better. There's also I don't know if these two pieces of information are connected, but people have made ASR work without tones. The Hausa example that I showed you there. People have also trained Yoruba systems with where tones are not explicitly marked. It's I don't yet understand the connection between these two facts. Maybe it is that tone is bearing less of a functional load in Bribri, that it can be more safely ignored than the contrast that you said. So the phonemes of Bribri map fairly well to the phonemes of English. Like there isn't an aspiration distinction, as you said. There isn't, Bribri doesn't have many phonemes absent in English. Like there's a retroflex R, for example, but that's the only retroflex. Maybe and tones, Bribri words can only have one tone per morpheme. So it isn't quite like Mandarin Chinese where every syllable needs to have a tone because every syllable could potentially be a morpheme. So maybe this is it because there's more tones that could be neutral in Bribri. And because the tones themselves have less of a functional load, maybe they can be more safely ignored. And the phonemes just map better to the English. I'm not sure. It's just a matter of, English was trained on more data.
It could just be that, yeah.
It could be. I haven't tried transfer learning with, Spanish, French, and Hindi would be next if I can find a good deep speech model for that one. Because, again, like French and Hindi, nasal vowels. Spanish, similar vowels. Like Bribri has 7 vowels. They're more similar to the Spanish ones than to the English ones. Yeah, there's a lot of more experiments that can be tried, but I'm still trying to find a better hypothesis than English is just trained on more things.
Well, that might be the case though.
Maybe.
Okay. Do we have some other questions?
If we don't have a question yet, I would love to. May I ask you to turn your cameras on so that I can ask you all a few questions and get to know you?
Sure, yeah.
Yeah, well, first of all, nice to meet you. Let's see. Could you raise your hand if you're working in a language from Europe?
From Europe, yeah.
Yes, from Irish to, yay. Could you raise your hand if you're working in a language from Africa? Oh, yeah, which one?
It was Amharic.
Hi, I can hear you, yes.
Yes, it is Amharic. So in Ethiopia. Yep.
Oh, I'm Amharic from Ethiopia, cool. Could you raise your hand if you're working in a language from Asia, Southeast Asia? Yay, let's see, Priya.
Yeah, so I'm working with Maghi and Bhojpuri languages and the Eastern Indian languages. So basically these are less resource languages, under-resourced languages.
Yeah. Let's see, could you raise your hand if you're working with a language from the Americas? Awesome, Francisco.
I'm not that much, but a bit with Mapudungun.
Oh, Mapudungun, yeah. Are you from Chile?
I'm Chilean, yeah.
Oh, cool. I'm Costa Rican. Yeah. Could you raise your hand if you're working for a language in Asia Pacific, Australia, Polynesia, Papua New Guinea? Yeah. So I mean, let's see the elevator speech for the other one. So there was a colleague of mine. I worked in New Zealand for a couple of years, and there was a colleague from the Cook Islands who. She's in a situation that must be familiar to all of you. She approached me and said she had done her dissertation in the grammar of Cook Islands Māori, and she had a ton of recordings, and she was like, I'm going to die before I finish transcribing this. Can anything be done about this? So that's what we're building the speech recognition for. And to be honest, that one is, we're lucky in that one can truly be called community-oriented research, because the work that I've been doing there has been because the community has asked for it. Like we're making OCR for that one because the library needs to scan a bunch of documents. We made the part of speech tagger because the teachers needed it for their linguistics of Cook Islands Māori class. The speech recognition again is to help Ake so that stuff is transcribed during her lifetime. And we're getting, yeah, I mean, we're in the threshold of like 30% character error rate. We're applying to a bunch of grants right now to get to the point where we can have, a good 20 to 30 hours of transcribed audio, because right now we have 3. So that we can turn this from a fun toy into something that she can actually use in the documentation. So that's something from Polynesia. So let's see, could you raise your hand if you work on the semantics, discourse, pragmatic side?
Yeah.
Yay. Oksana.
Yeah, well, a little bit. I work on diachronic word embeddings mostly for Irish, but for basically any historical language. So, yeah.
Awesome. Could you raise your hand if you work on syntax morphology? Nice. Let's see, Delphine.
Yes, so I'm actually working on the Alsatian dialects, which are spoken in France, Germanic dialects from France. And yeah, we're trying to make universal dependencies corpora.
Oh, amazing.
Yes.
Yeah. And could you raise your hand if you work on audio, speech recognition, alignment stuff? Nice. Elizabeth.
Yeah, I'm a PhD student, mostly working in the NLP side of things, machine translation and speech recognition, sometimes combined.
Awesome. Do you work in a particular language, family of languages, or?
Unfortunately, it's usually the ones that have corpora rather than dictated by my interests. So a lot of what I've been doing recently is trying to better create and align corpora automatically so that I can branch out a bit more. But yeah, most recent things have been Spanish or German or Swiss German.
Awesome.
And
I mean, corpora is good. I think we can all agree on that.
Yep.
Yeah. And I mean, yeah, no, I'm super thankful for the invitation and for getting to know all of you.
Huh? Yeah, it's a very interesting group. So I mean, we advertise this call, through our network. So we have a lot of people from Ireland and then a lot of people from around Europe, and yeah, a lot of interesting research everyone's doing.
Yeah.
Okay. Well, great. So I think that's a really interesting talk and a really nice discussion afterwards. So I'd just like to have to say thank you again to Rolando, and it's an amazing talk. And
here's hoping to meet you all in person at some point in the future.